Many of you know I haven't always been a data scientist. I actually studied chemical engineering as my undergrad and even worked for ExxonMobil, who is a huge manufacturing and engineering juggernaut. When I first was breaking into data, I wasn't even really sure how data could be paired with manufacturing and engineering. I didn't even know if it was possible, and I didn't know what to do to figure all that stuff out. And so in this video, I'm going to show you an example of how engineers could potentially use data in their job. We'll have a replica data set with some manufacturing data that deals with basic raw material characterization. You can think of this as some sort of mining facility data or plastic making or rubber making data, or maybe even a metal polishing process data. And we will try to figure out how to increase the favorable outcome, how to actually make what we want to happen with data. This is also part of my series of doing 30 data science projects in 30 days. So it would be a great project that you could have on your portfolio if you're trying to transition into the data field, perhaps from the engineering and manufacturing field. By the way, if you want this data and you want the code that I'm about to write so you can replicate this project, look in the description down below and you should find a link where you can get the code for absolutely free. Let's get into it. So here's what our data set looks like. We have a bunch of different lot numbers over on the left-hand side, and here are the outcomes in B, okay? These outcomes are given by an engineer who has lots of experience, who's done this a lot of times, and basically using the eye test is able to judge the outcome as either adequate or poor. Next, they take 6 different measurements: size 5, size 10, size 15, TGA, DSC, and TMA. These are 6 different measurements they take for each one of the different lots, and they basically test it within those lots. And our goal is to be able to use data to help this process come with more adequates for an outcome and less poors. This data and this example is actually taken from one of my favorite free resources about all things data, especially when it comes to engineering. It's called Process Improvement Using Data by Kevin Dunn. It is a free resource. It's available at learnche.org, or you can check the resources section down below. I highly recommend it. It is totally free. And today's example comes from that section in the book about multivariate modeling. So you create a product at this company, but your product is becoming a little bit worse and you think it might be because of a key raw material, but it could be your process conditions, you're not sure. So you're going to begin by investigating the raw material supplier. You basically have the data that I showed you earlier that basically shows the 3 different measurements. The first 3 are the size values for plastic pellets. The other 3 are thermogravmatic analysis, differing scanning calorimeter, and thermomechanic analysis measured inside of a lab. This is basically allowing you to adequately characterize the raw material. Also notice that there's the adequate or poor that basically reflects the process engineer's opinion of the yield that comes from that lot of material. So what it asks us to do is build a latent variable model for all observations and use AutoFit to determine the number of components. Okay, if you don't have AutoFit, use the Pareto plot to plot the number of eigenvalues to decide the number of the components. So what we're going to do with this data set is we're going to try to study it and try to figure out how can we get more favorable outcomes. And we're going to be using something called PCA, or principal component analysis. Now, I don't have time to dive into the nitty-gritty of PCA. I'll let you use this awesome resource that we're using, the process improvement using data, or check out StatQuest. Josh Starmer has a great video on PCA, the actual nitty-gritty of it. We're going to be using PCA in R to evaluate which of these 6 characteristics could potentially really influence whether we have a adequate or poor outcome. I chose to do R for this analysis. No real reason other than I want to get better at R. You can do the exact same thing in Python. I actually think this is most easily done using something called JMP from SAS, but that costs a lot of money unless you have a license at your company. I think it's one of the best people that do it. So we're just going to be using R, which is more than sufficient to tackle this problem. So the first thing we need to do is download the CSV and get it uploaded into R. I use that using the read.csv and then calling it data. Next, I changed the row names, which is basically the index of the data. Instead of just having a 1, 2, 3, 4, I combined the lot number and the outcome so that would basically represent the index of that particular row within the data set. The reason I did that was just so that it would be a little bit easier. So you see how these are combined now. It's going to be a little bit easier when I actually do some of the graphing because it bases it off of the index. So that was done by experimentation. I figured it out eventually. Next, I did the principal component of the data inside of the size and the TGAs basically, right? Because we can't do PCA with lot number and outcome. We need numbers for PCA. So these 6 columns were included in the PCA. We took the principal analysis of those and did scale equal to true so that they're all on a 0 mean, 1 standard deviation basis. That's one of the steps you need to do for PCA before you get going. And we stored that inside of results. Now, next inside of the challenge, you'll see that they asked us to figure out how many principal components we should be using. The way I did that is right here. I found this formula online. This basically shows the percentage of variance that is captured by each principal component. So 44%, then 34%, and then 14%. And the next one's 5%. So we're above 10% on all 3 of these. So 3 is probably the most appropriate number. We can also get a hint that 3 is probably a good number because in step 2, it says interpret component 1, 2, and 3 separately using the loadings bar plot. And so that's what I've done here is I've created a loadings bar plot that basically this shows for the first principal component, which once again captures like 45% of the variance, what is the most important factors? And turns out size. You can see that size is contributing almost equally across those to the first principal component. The second principal component is the TGA and the TMA. Those values are above 0.4 in magnitude. And then the third principal component is the DCS. So basically, we have one that represents the size, the second one represents the TGA and the TMA, and the third represents the DSC. So those are the 3 principal components that we have for this project. We've now shown the bar plot, and we've also decided how many that we need. And the last thing it asks us to do is to do the score plot and color code based on the outcome and see, what's basically going on with the contributions. So what that is called actually is called a Biplot, and I was able to make one right here. And what this does is it has the 2 different score values from the PC1 and the PC2, and the labels are shown by the index. So you can basically see I know it's a little bit crowded. What you're basically going to see is that there's a bunch of pores over here on the left-hand side. Pore, 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 pore on the left-hand side. And then a lot of adequate kind of over here in the middle, okay? And if we want to have less pores, we can see what is influencing the pores. And those are close to the size arrows. So that way we know that the size arrows basically is the sizes is what's affecting it and making it poor. It doesn't look like there's a huge, there is a little bit maybe in the DCS because there's a little bit of vertical action, but a lot of it mostly looks like it's on basically close to these size values. Basically, we could take this graph and show our boss and say, hey, look, all of these pores are around the same direction as the size values. So the size values is what we really have to hone in on so that we make sure that we have adequate and good outcomes. Our boss is going to be so happy, going to give us $1 million raise, and we can ride off into the sunset. And by the way, if you want to do more data science projects, I would suggest checking out these 2 videos right here and subscribing to my channel because I'll also give you $1 million raise.